Hello, welcome to Basics of Finite Element Analysis Part 2. Today is the second day of this fourth week of the course. Yesterday we had introduced the need to have a weak form of this two-dimensional equation, partial differential equation having one variable, and that is what we will continue to do today. So, to recap, what we had developed was, this is our equation A is the basic equation which we will try to solve. For this equation we had developed a weighted residual statement which is equation B, and another form of weighted residual equation is equation B1, and we had said that as per equation B1 the differentiability requirement on U is of second order. So, now we will try to weaken the differentiability by developing a weak form of equation B1. So, we will develop weak form of B1. So, before we do that, what we will do is we will write down 2 or 3 important relations. So, we will note, so what we note that del over del x of w times f1 is partial derivative of w with respect to x times f1 plus w times partial of f1 with respect to x. So, this gives me w times partial of f1 with respect to x equals this relation. And likewise, similarly, w times del f1 over del y equals del over del y w times f2, oh excuse me, this should be so w times partial of f2 with respect to y equals partial with respect to y of the multiple of w and f2 minus del w del y times f2. So, let us call this equation C1 and let us call this equation C2. So, this is equation C1 and C2 we get by rule of differentiation of two functions multiplied to each other, right, differentiation by parts. Also, recall the component form of divergence theorem. So, some people also call it gradient theorem, and it has the same theorem can be expressed in a vector form or in a scalar form. So, a scalar form is known as the component form because there we are taking individual components and write them as separate equations. In vector form we assemble them and write it into one single equation. So, this component form of divergence theorem we had actually developed in FEA part 1. So, if you do not remember, kindly go back and check some of our old lectures and you will see all the details. So, here what I will do is I will directly write that result. So, the component form of that divergence theorem says that if I have an integral of partial derivative of, let us say, any function w times f1, okay, then it is nothing. So, this left hand side is an integral over the domain of the element. So, this I can express it as a boundary integral of w times f1 times nx ds, and I will explain this in a minute. And similarly, integral of del over del x, del over del y, w times f2 dx dy equals boundary integral of w f2 ny ds. So, what does this mean? What this means is that suppose I have a domain, suppose I have a domain. Now, in reality this domain will be either a triangular element or a square element, but this equation, so let us call these equations as d1 and d2. This equation is valid for any boundary, you know, it can be any complicated boundary, it does not matter, it does not have to be a triangle or a square or rectangle, it is valid for any boundary. So, what this says is, let us try to understand what is equation d1. The left hand side means that if I at any point p I have a value of f1, because f1 is a function of x and y, right, f1 is a function of x and y. So, if I take that function, that value f1, I multiply it by weight function, that is also a function of f and x and y. So, at any point p I calculate this product w and f1, and then if I differentiate it with respect to x, partially differentiate it with respect to x, so I will get some number, right, and then I integrate that function over the domain. So, this entire thing is the domain. Then that integral can also be evaluated by finding the value of w and f1 on the boundary. So, this is my boundary. So, I do not have to find all the values of f1 and w in the domain, but I can also calculate the left hand side by using the right hand side equation by finding the values of f1 on the boundary. So, let us say this is another point p2. So, this will be clearer. Let us say this is point p2. So, what do? I find out, first thing is that I find out what is the direction cosine of a vector which is normal to the surface. So, this is my n vector. So, for any boundary shape at every point it is known, this n is known, because I know the shape of the surface, right, I know this shape. So, I know the edge of the boundary. So, at every point I know what is the direction of this n vector, which is a unit normal in the normal direction, right. Then it will have an x component nx and it will have an ny component, okay. So, I can calculate nx and ny because the outside surface is known. If outside surface or edge of the surface is known, then at every point I can calculate nx and ny because I know the shape, actual physical shape of the system. So, I calculate at every point nx, I multiply that nx with f1 at point p2 and also I multiply that by w at point p2 and I multiply it by a small length, this is ds. Okay. So, I do these computations all along the boundary. So, I get a boundary integral which represents the left hand side. So, a surface integral which is of this form can also be calculated using a boundary integral. This is what the divergence theorem means. It can also be calculated using a boundary integral. Okay. This is something similar we also did when we were doing one dimensional equations, where we computed an integral along the length of a line in terms of boundary values at the termination points of the line, right. So, here also we are calculating the integral in terms of some parameters which exist on the boundary. Okay. So, this is what the divergence theorem says that if I have a surface integral of this form, not of any general form, of this form which is shown here, which is on the left side, then I can calculate the value of that by using a boundary integral by evaluating all these parameters w, f1, nx and integrating the multiple of this all along the boundary. Okay. So, this is what it means, it is very important theorem. And one thing I wanted to say is that if this n points outwards, then it is positive. This is the convention. If it is pointing inwards, then it is negative. Okay. So, what we will do is we will first put C1 and C2 in equation B1. We will first put C1 and C2 in equation B1, and because of this, this term will get replaced by this term, and also this term will get replaced by this term. This is the first step. So, that is what we will do. So, we put C1 and C2 in B1. So, what do we get? So, W times del over del x of F1, right, this is this term. So, this get replaced by this thing, and there is a negative sign here. So, I get minus del over del x W F1 and then plus del W over del x F1. Okay. So, I have put C1 in equation B1 and then I put equation C2 in equation B2. So, I get minus del over del y W F2 plus del W over del x del y F2. And then these terms do not change. So, I still have A00 u W minus F W dx dy equals 0. So, next what we do is put d1 and d2 in equation E. So, this is equation E. So, what does that mean? That I am going to replace this term. This term is same as this term. So, it is a surface integral, I can replace it by a boundary integral. Similarly, this term and this term are same. So, I can also replace these two surface integrals by two boundary integrals. So, first I will write the surface integral terms and then I will write boundary integral terms. Okay. So, I have del w over del x times f1 plus del w over del y times f2 plus a00 u w minus f w dx dy. These are the surface integral terms, and then I put boundary integral terms. So, this gamma e represents the boundary of eth element. Gamma represents boundary and e represents eth element. So, this equals minus w f1 nx plus w f2 ny ds equals 0. Okay. So, I can again rewrite this as integral of. So, f1 now I am going to replace by the original definitions. So, this is wx times a11 ux plus a12 uy plus wy means del w over del y times a21 ux plus a22 uy plus a00 u times w dx dy equals this term, and these terms I will take to the right side. Boundary surface integral of w times f dx dy plus boundary integral of w a11 ux plus a12 uy and x, excuse me, plus a21 ux plus a22 uy and y ds. So, let us call this equation f. So, on the left side you have these boundary terms, surface integral terms, and on the right side you have again a surface integral term, but you also have a boundary term. So, again to draw comparison, in our 1D formulation, when we did a weak formulation, we weakened the differentiability of the primary variable of variables, right. And when we did that, in the process of weakening of differentiability, we used to get some boundary terms. We are seeing that the same thing happens in the regular strong form of the weighted residual statement. This is the strong form, okay, or this is the strong form because the differentiability requirement is higher. Here there are no boundary terms, but when we weaken the differentiability, we get some boundary terms in process, okay. And these boundary terms help us understand what kind of boundary conditions we need to know to solve this problem. So, let us look at the boundary terms. So, in this boundary terms, the first thing we have is W. W is the weight function, and in context of 1D problems which we had discussed, it could also represent as the, so this is weight function, and it could also represent as variation of primary variable. It could also be interpreted as a variation of primary variable. So, if the primary variable is known on the boundary, then the variation is 0. If the variable, if at any point, if the value is known, then it cannot vary, So, then the variation will be 0. So, what this tells us is that, so this is primary variable. So, what this helps us understand is that U is the primary variable. U is the primary variable, and if I specify this variable, then specification of U implies that I am specifying essential boundary condition or EBC. So, in the boundary term, either we specify W or we specify the other part. Okay. So, this is one thing. The other part in the boundary condition is this thing. Okay. So, this is A11 Ux plus A12 Uy Nx plus A21 Ux plus A22 Uy Ny. Okay. This I can abbreviate it as Qn. Now, this Qn, what does it mean? It means, so this is the direction cosine in x direction, this is the direction cosine in y direction. These are the components of the direction unit normal. Okay. So, this term represents the projection of an entity. See, this term represents projection of an entity in the x direction, and this represents in the y direction, right. So, what this means is that Qn, it represents projection of a vector, it represents projection of a vector, and what is that vector? Vector will be A11 Ux plus A12 Uy I plus A21 Ux plus A22 Uy j. If I project this vector in the direction of n, right, if I project this in the direction of n, why? Because n is what? Nxi plus Nyj, right. Then when I project it, what will I get? I will get this same thing Qn, right. If I take a dot product of this vector, and this unit normal, then I will get Qn. So, it represents projection of this vector in the direction of n, that is unit normal direction. unit normal direction on boundary. Okay. So, what does, so when we are specifying the boundary term, either we specify u, if u is known then w will be, if u is known then w will be 0 because it represents the variation, right, it represents variation, or if u is not known then I have to specify this thing. So, either we have to specify, see the boundary term has two terms w and this entire thing in purple. So, either we specify u or we specify this entire thing in purple. So, this is, so qn is secondary variable and if I specify it, I say that specification of qn implies that I am specifying natural boundary condition. Okay. I am specifying natural boundary condition. So, this is what it means. So, I have two boundary conditions, one involves the primary variable which is u, the other involves, and if I specify it then I say that I am specifying EBC or essential boundary condition, or I specify qn which involves natural boundary conditions. So, this concludes our discussion for today and we will continue this discussion on weak formulation tomorrow as well. Thank you.